In this video, we're going to see how to generate the inverse hyperbolic cosine function using the CORDIC algorithm. Now, there's a lot more involved in this example than in previous examples, and in fact we're going to have to work through the CORDIC algorithm 4 times. So there'll be a step 1, step 2, step 3, and on the next page you'll see there's a step 4. Now again, we're going to use an identity in order to generate this. Now the identity is arc cos of x is equal to the natural log of x plus the square root of x squared minus 1, and this is true for x greater than or equal to 1. Now again, I'm not going to prove this identity, and I'm asking you to accept it, although we will have a look in the graphical calculator and we'll see that it is actually true. Now in the previous video we worked out how to generate the natural logarithm of a value, so we know how to do this part here. But how are we going to generate the x plus the square root of x squared minus 1? Well, let's look at the very first step here. In step 1 we're going to use the hyperbolic vectoring mode. Now don't worry too much about the mathematics here, we'll talk through it first of all, but again we will go through it within the graphical calculator in just a moment. So from this hyperbolic vectoring mode, the output xn is equal to an the square root of x naught squared minus y naught squared. So what we can do is we can knock this into the correct format. If we make the x naught equal to some value, let's say we just call the value for the moment a, and we let y naught equal 1, then what we'll be left with is an times the square root of a squared minus 1. So this is really in the same format as this part here. The only difference is we have this extra factor of an, which is our gain factor, which for hyperbolic vectoring mode is approximately equal to 0.82816. So let's choose an actual value that we're going to work with. Now the actual value we're going to work with throughout the rest of this example is 1.3. So we're looking to find the hyperbolic cosine, inverse hyperbolic cosine of the value 1.3. Now, for the first step here, we're going to set the value of x naught is equal to a, which is just our 1.3. The y naught is going to be a value of 1. That means that the output that we expect to see is going to be the an times the root of 1.3 squared minus 1, which is equal to 0.688. So that's going to give us this factor here in effect, but it's going to give us this factor multiplied by this value of an. Now what we want to do is we want to get rid of this value of our an, and also what we want to do is add another factor of our x. Now for the x we'll just replace it by the value of a, okay? So we want to get another factor here added on. So in order to do that we can go through to step 2. Now step 2 is going to use the division algorithm that we've seen in a previous video. So we're going to be using the linear vectoring mode. In the linear vectoring mode we're going to have a value for Zn, which is an angle, which is equal to Z0 plus Y0 upon X0. Now what we can do is we can choose the value for X0 is equal to An. So in effect we're going to be doing the division, so we will divide out this An factor. And in the top line our Y0 will be the output of the first stage, which will be our 0.688. And the value of our Z0 is going to be the value of our A, which is our 1.3, but remember that's going to be in a value in radians. So it means that what we're going to have then, after this stage is completed, we'll have a value of A, which is 1.3, and we'll have a square root of A squared minus 1. So that is going to be 0.83066, so we should get a value of 2.131. So that's us generated what we require inside this bracket. Now we're going to have to go through the last two stages. Now the last two stages are just performing the natural log, and it's the same two stages that we've seen in the previous video. So in order to generate the natural log, we're going to use the hyperbolic vectoring mode. In the hyperbolic vectoring mode, we're going to set the value x0 is equal to a plus 1, y0 is a minus 1, and their value for a is the output from the previous stage, which is a value of 2.131, and we have our angle z0 is equal to 0. So what we'll get at the end of this is the half of ln 2.131, which is 0.378. So in actual angle terms, that's equivalent to 21.5778 degrees. But remember, now that we've worked through the natural logarithm, we've only got the half of the natural log of this number. So what we're going to have to do is we're going to have to multiply it by 2 in order to get the actual answer. So we'll see that on the next page. So the final step is step 4. So we're going to have to multiply by 2. So again, we use the linear vectoring mode, and we'll have our Zn is equal to Z0 plus Y0 upon X0. And what we can do is we can set our X0 to a value of 0.5. And the Y0 is the output of the previous step, which is 0.378. So we should get a value of 0.378 upon 0.5, which is equal to 0.756. Now if we actually work out the arc cosh of the value 1.3, you can see we do get this value 0.756. So that means that our mathematical algorithm gives us the correct answer. But what we want to do is actually work through it in the graphical calculator and see whether we get this final value of 0.756. So let's go ahead and we'll do that now. So we start off with the inverse hyperbolic cosine function, which is in pink. And you can see that this is valid for values of x greater than or equal to 1. Now, the identity tells us that this function is the same as the natural log of x plus the square root of x squared minus 1. So now if I plot out this new function, you'll see it will sit exactly on the top of the original function. So you can see that this is the identity here shown in the green colour. So it means that we can see that the arc cosh x is indeed equal to the natural log of x plus the square root of x squared minus 1. So the identity is correct. Now the point that we are interested in and we're going to use in our example here is 1.3. So when we go to 1.3, the inverse hyperbolic cosine for 1.3 is 0.756. So this is a final answer we're hoping to get when we run through our CORDIC algorithm. So we start off with our step 1, which is the hyperbolic vectoring mode. We have our value of our input, which is a is equal to 1.3. So this is the x0 value. So I'll put that in just now. And the value for our y is a value of 1. Now we're using the vectoring mode, So what we want to do is we want to add and subtract the correct angles in order to ensure that this value here for our y tends towards 0. So I'll go ahead and start subtracting and adding these angles. So you can see that the final value for our xn is 0.688. And this is the value that we were expecting to see from the calculated value up here, which is 0.688. Now in step 2, we're going to perform the division by an, and we're going to add the value of a. Now we're going to be using the linear vectoring mode, and in this mode we're going to have an angle at the output which will be z0 plus y0 upon x0. Now we start off with the value x0 is equal to an, which is our gain factor. So this value is 0.82816. So that's the value for our x. Now the value for our y is going to be the output from the previous stage. So that's going to be 0.688. Now again, we're going to be using the linear vectoring mode. So we're going to look at this height here, which is our y, and we're going to add on and subtract off the requisite angles in order to ensure that this value of y tends to 0. So let me go ahead and I'll do that now. So you can see the value of our y has tended towards 0. But in this mode, the final output we're interested in is our value of an angle, which is the angle Zn. Now in order to get that angle, we have to add on and subtract off the values of the requisite angles within the linear vectoring mode. Now I've already gone ahead and done this down here, and you can see the angles that we're going to be using. Now one thing to note here is we're actually starting off with this angle here, and you can see that's 74.48 degrees. Now this angle here is the value for our A in radians. So we're going to have an angle which is 1.3. Now 1.3 in radians, that is, we multiply it by 180 and we multiply it by pi and divide by 180 will give us 74.48451. So we start off with this, and this is our first angle. And then we add on and subtract off these angles here. And of course, we add and subtract depending on whether the value here is going to be a positive or a negative value for our y at each iteration. So let me go ahead and I'll add and subtract these off just now within the simulator. So the final value here for the angle Zn is equal to 122.156 degrees. Now whenever we convert this back to radians, we get a value of 2.132. So we're not very far out. The value we expected to get was 2.131, but we're now actually getting a value of 2.132. So let's move on to the next stage. So in the previous two stages, we've generated our x plus the square root of x squared minus 1. Now what we have to do is work out the natural log of that value. So again, from the previous video, to work out the natural log, it's done in 2 stages. So this first stage is going to be this step 1. What we do is we set the value x0 to the value of a plus 1. Now the output a again was the output from the simulation, and it was a value of 2.132, so it wasn't far from the actual value. So I'll put that in just now. So we're going to have the 2.132 plus the 1. So we're going to have 3.132 for our x value, and we're going to have our 1.132 for our y value. And the value for our angle z is equal to 0. So again, we're using our vectoring mode. So what we want to do is we want to make sure that the value of our yi tends towards 0. So we add and subtract off the requisite angles for the hyperbolic vectoring mode in order to do that. So let me go ahead and I'll do that now. So you can see the value of our yi is tending towards 0. But again, what we're interested in here is the angle Zn. Now I've already worked through this example and I've worked through the value of Zn. So what we have to do is we have to add and subtract off the relative angles for this particular vectoring mode. So these are the angles here. So let me go ahead and I'll put those into the calculator. So the final angle that's generated here, which is our Zn, is going to be 21.5778 degrees, which when we convert it to radians will give us a value of 0.376. So you can see here we're very close. The calculated value is 0.378 and our simulated value is 0.376. So let's move on to the final stage. So finally, in step 4, we're going to multiply by 2. Now, in order to multiply by 2, this is the same as dividing by a half. So we can use the linear vectoring mode in division in order to generate this multiplication. So we can say Zn is equal to Z0 plus Y0 upon X0. The value for our X0 will be 0.5, and the value for our Y0, well, our Y0 was 0.3766. And you can see that was very close to this calculated value, 0.378. So let's put our values in just now. So we're going to have our 0.5 and a value for Y 0.3766. So now what we want to do is we want to use vectoring mode, so the value for our yi has to tend towards 0. So let me go ahead and I'll add and subtract off those angles to make that so. So you can see the value for our y has tended to 0. But now what we are interested in is the output in terms of the angle Zn. So what I have to do again is add and subtract the angles depending on whether the value for our yi is positive or negative. And you can see that I've actually already worked through the simulation, and these are the angles which we add and subtract. And they're going to give us a final angle of 43.196 degrees. So let me go ahead and I'll put those in just now. Now the final angle for Zn that we get here is an angle of 43.196 degrees. Now whenever we convert that to radians, we get the figure 0.754. Now you can see here that the actual value that we're expecting to get is 0.756. So let's summarise our results on the next page. So we have our 4 CORDIC algorithm steps, we have our calculated values and our simulated values. Now the one we're interested in really is the final value here. So the final calculated value for our inverse hyperbolic cosine is 0.756 and the simulated value is 0.754. So let's plot these out. So we have our inverse hyperbolic cosine function here. At the value 1.3, we're expecting to get a value of 0.756, but our CORDIC algorithm has given us a simulated value of 0.754. So you can see that this process works and it gives us a good approximation. Now the inverse hyperbolic cosine and sine functions are 2 of the most difficult ones that we're going to produce using the CORDIC algorithm. So in the next video we'll go on and we'll see how to produce the inverse hyperbolic sine function. So thank you for listening, I'll get you on the next video. Goodbye.